in our study of probability so far, we know kind of the fundamentals, right? We know the four rules. You know, all probabilities have to add to 1. They're non-negative. You can add disjoint events, etc. And in reality, that allows us to do a bit, but not a whole lot, because things are a bit more complicated than just saying that this can happen or this can happen or what are the outcomes, and we can try and package it all into one thing. Likely there are going to be things that happen that influence things later on, or things can happen simultaneously, etc. So we need to develop some additional skills, okay, and learn how probabilities are influenced by the interaction of events. And so the first of these techniques that we're going to look at, I guess, before going on, we're going to look at probabilities for 2 events in all 3 of these videos. Know that if you have more than 3 events occurring, that's a little bit of a different story. You can do it, but it's just a little bit more. So we're going to look at one event that looks that takes into account one event happening and how it influences the next event occurring. And when we talk about that event that has already occurred, we call it as a condition, something that we're conditioning upon. We're saying that this condition has happened, and given this, what is the probability of this other thing happen? And that is conditional probability. Okay, so we're saying we're looking at, again, the probability that B occurs, right? If or given, oh, typo, given that A has already occurred. Okay, so A occurred, and then we're looking at B. And you can reverse these two. These are just general. But how we calculate this mathematically is we restrict our sample space to just be the sample space for A, look at the probability, or out of that probability occurring, what part of B occurs out of that. So, and that actually ends up being the intersection. So if we think about a general Venn diagram, okay, let's say here is A and here is B. Okay, what we're going to do is, for the probability, since we know that A occurs, right, we're looking already in just this part of our sample space, right? We're saying that A occurs, and then if A occurs, what is the chance that B happens? So out of this entire piece, the component that represents where B is happening is this middle piece, right? So we're looking at this little sliver, probability of A and B occurring, out of P of A. Okay, so that's kind of the idea where the definition came from. Okay, so with this idea in mind, let's get working on an example. Okay, so I'll give you a minute just to read through this and kind of digest it. Resume the video when you're ready. Okay, so we have our first task is to identify the 3% in the prompt as probability. So we have this number, 6.3, and the 0.7%. Okay, and for ease later on, I'm going to express these in decimal form. So we have, something is equal to 0.003. We have another thing equaling 0.007, and we have another thing equaling 0.063. Okay, and so then I'm going to need probability statements, right? Probability and probability. Okay, so what is this 0.003 meaning? It's currently living with HIV, so I'm going to call this probability of HIV, and I'm just going to define this event as U.S. population living with HIV. Okay, whenever you introduce symbols or events, you should name them just so we're all on the same page later on when we're looking back at this. And similarly, this 0.07% corresponds to hepatitis hepatitis C. So I'm just going to say HCV is U.S. population living with or has had Hep C. Okay. And then let's see. So it says for those living with HIV, 6.3%. Okay, now this one might take a little bit of time and energy to digest. So we're saying that this number represents the probability of having HCV, right? That's the probability, because what we know about this group of people is that they are already living with HIV. Okay, so that's a given information. That's our existing condition. So we're saying we're not looking at the entire population. We're just looking among those with HIV, right? So we're restricting our sample space to be just among those with HIV. Okay, and then out of that population, what part is living with HCV? All right, so there we have some numbers, and then now that's all we had to do for part A. For part B, it says what is the probability that a randomly selected U.S. member of the population is currently living. Okay, so I'm just gonna start writing this probability that a randomly blah 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 currently living with HIV, right? And is living with or has had HCV. So that's the event HCV that I've defined. Okay, now how in the world do I calculate this? I have no clue. So what I'm going to do is I'm going to play. I'm going to play with this conditional probability up here. Remember, when we write this conditional probability, this is the same as probability of the intersection, or the probability of their simultaneous occurrence, HIV, over probability of HIV. Okay, and now what's really neat about this is I need HIV and HCV, right? So then that actually pops up right here. So I can use this number, and I know probability of HIV. Okay, so I just maybe need to manipulate this a little bit more. Okay, so this is equal to 0.063. So what I'm just going to do, I'm going to leave that off to the left, and I'm going to do a little bit of side work. So probability of HCV and HIV over probability of HIV is equal to 0.063. And what I'm going to do is actually insert that number here. So probability of HIV was 0.003. And now I can just solve by cross multiplying, or multiplying both sides by 0.003. And if I do that, I get 0.30189. And yeah, very, very tiny percent. Okay, so there we go. Okay, this is a small number, but keep in mind there's 330 million people in the U.S., so it scales up a little bit. Okay, but nevertheless, we solved our problem. Okay, and then lastly, part C, what is the probability that a randomly selected member? Okay, probability statement is living with HIV if they are living with, so if we always translate as a bar for the conditional probability, because this is the condition that follows, HCV, okay? And so then if I calculate this, I just use the definition, so probability of their simultaneous occurrence and HCV all over probability of HCV, okay? And this is where part B was really useful to find that number first. So this was 0.000189, and then I divide that by probability of HCV was the 0.007. And I can punch this into a calculator and get that the answer is 0.027 or 2.7%. Okay, either way. But nevertheless, the key step here was using the definition of conditional probability to kind of dissect this conditional probability. Okay, and then we use that to find this simultaneous occurrence. Okay, and that manipulation that we ended up doing here in part B, that actually can be done in general, and that gives rise to what we call the general multiplication rule. All you have to do is, take the P of A that's in the definition of conditional probability and multiply it to both sides. And that's okay as long as P of A is not 0, or bigger than 0, I should say. So there we go. That's a nice little rule, but the major idea is that idea of conditional probability, how we restrict our sample space to be just the piece of the space that we know has occurred.